So this chapter is about oblique shock waves. So unlike normal shock wave, where the flow before is supersonic and after is subsonic, here in oblique shock wave, the flow before is supersonic and the flow after is?
We don't know.
We don't know. It could be subsonic or supersonic, okay? We'll see how we can calculate that. And so our job in this chapter is, if we know the pressure, temperature, and Mach number before the shock, we need to calculate the pressure, temperature, and Mach number after the oblique shock wave, right? So in this course, basically, we will only consider 2D wedges. This is not the axisymmetric case. When you have like a rocket, that will be a little bit harder. So let's take the easy one. So the easy one is like 2D flow. Basically, we are thinking that this wedge is basically have infinite depths, all right? And we'll see how the axisymmetric one will be calculated later. But we will be only concerned with 2D wedges, all right? So as you can see, the flow before the oblique shock wave has to be supersonic, of course. And he would, before the shock wave, he's not even aware there's a wedge. And then suddenly when he crossed that shock wave, that red line, it's not red in real life. When he crossed that line, he suddenly changed direction and moved with, this is very important, he moved with the new direction. The new direction is the wedge geometry. So before, he's moving horizontally, unaware of what's going to happen, and after, they are all moving basically in the new direction. So because of this, that wedge, the half wedge angle delta, it actually, there's even a better name for it. What would you call it? What is even a better name than the half wedge angle? Delta, you would call it?
Delta over 2?
No, you would call it the deflection angle. Right? Why deflection? Because really the flow get deflected by this much. So delta is the deflection angle. Why I'm saying this? Because sometime we will see the supersonic flow, just turning without actually seeing the wedge. Like this, if the picture is only the upper part of it. Say, let's imagine that the picture is only, the problem is basically something like this. Only that part is in the problem. You will be able to say that, there must have been a wedge with that angle down there that made that shock wave, that oblique shock wave, right? So even if you don't see the wedge, the angle that deflect the flow, that's what we're going to use in the solution, right? And of course this angle match the geometry where it's coming from. In even other problem, there could be really no wedge. It just, there is high pressure underneath or something that caused that deflection, and that will still generate an oblique shock wave. So what I'm trying to say is that any time the supersonic flow changes direction, it will happen over an oblique shock wave. Okay? So delta is the half wedge angle, the deflection angle, those are names for it. Theta, which is different from delta, theta is the shock wave angle, okay? And we need to realize that they are different, right? So now the flow before the shock, horizontal, the flow after the shock, moving with delta. So we know M1, we'd like to get M2 and P2. What's P2? That's the pressure after the shock. So before there is one pressure, after is another pressure. So how are we going to get all this? How are we going to generate that table or the equation that the table come from? How are we going to get the solution? We will have to three what? Continuity, momentum, and energy equation. We will write those three equations, right? Solve them together, and the solution will end up being basically our set of equation / set of table that we will use, and the solution will be in appendix D. Very good choice, right? So it's going to be in appendix. It's actually appendix D is different this time. It's actually a graph, not really a table, but we will use it today. All right. So here is how it goes. So first of all, look at this. He split the velocity V1 and V2 into a normal component to the shock, a tangential component to the shock. The same thing for V2. Normal component, tangential component. V2 normal, V2 tangential. V1 normal, V1 tangential. Why he's doing that? Any reason for a free homework problem?
Oh, so
Did you get a free homework problem already today?
yeah.
You don't qualify for another one. There is a cap. There is a cap, one homework problem per day.
For you.
One homework problem per day per family.
So you can write.
The question is why he's splitting the velocity into normal and tangential component.
So
Jason.
you can write the V1 in terms of theta with sine and cosine, and then solve for the angle down there using geometry.
That's not the reason I'm asking. I'm expecting you to say no. I mean that's a step that we will do. But what's the main fundamental reason why we're splitting the velocity?
Because you gotta have your x and y components in your equation.
And you had a free John. What's your name again?
Nick.
Nick had a free homework problem. He said why we are splitting the velocity because he said you need the x and the y component of your equation. And to complete his statement, you need the x and y component of the velocity for the x momentum equation and the y momentum equation. Because he realized that the momentum equation is a direction equation. You cannot just write the momentum equation. It's the x momentum equation or the y momentum equation or the two of them. This time, we always used to write the x momentum equation, if you remember. In chapter 3 and chapter 4, we used to write the x momentum equation. Here, for the first time, we will write two momentum equation. Huh?
Jason feels cheated.
Huh?
Jason feels cheated. I think that's what he was saying.
Well, he said, let's solve for the angles. So he will get another free homework problem. Don't worry about it.
You're mad. Speak up.
He will get it. So anyway, the point is we need two momentum equation. Therefore, we need velocity component in the two equations. See, when it was like this, V1 and V2 wouldn't show up in one equation. In a single equation, they will not show up. But when we split them, we can write two momentum equation now. Why I split them normal and tangential? It's not important. I could actually split them in the x and y. But it makes sense to split them in the shock coordinate system. It makes the equation easier for us. So how we can split them in the normal to the shock and tangential to the shock? We have to find the angle that they are making. So for example, this is theta. How is that possible? So if this is theta, then what is this one?
Theta.
That's very good, right. And so if this one is theta, then why this one is also theta?
Because another triangle.
No, because these two are 90 degree and those two are 90 degree. So because of this, then this is equal to this. Alright? Alright? So it ends up being, this is being theta. Alright, so if this is V1 and this is theta, that make V1t is V1 cosine theta. And this guy is V1 sine theta. Alright? That's those first two equations over here. If I can just grab them. Alright? So this is basically this guy. Now you go to the V2. You need this angle. What is that angle? Yeah, you would think. No, it's not. See, this is delta. But this is not delta. This is... Actually, this angle is exactly this angle, right? What is that angle? Theta minus delta. Right? So we can actually write here that this is theta minus delta. And so then that make V2 normal is V2 sine theta minus delta, and V2 tangential is V2 cosine theta minus delta. We are done with the four velocity component. Are we ready to write the momentum equation or not yet? Anything missing? How we write the momentum equation? We say what's plus. Okay, we can say this is positive and this positive, and we make a control volume, and then what else before we write the momentum equation? Fluid 1, you know, when we used to write momentum equation, we put the control volume and we put what on it? The forces, right? We need to put the forces. So what forces are going to act? See, I'm picking the, let me get my cursor. So this dotted thing over here, that's my control volume. I'm taking a slice, or basically I'm surrounding the shock wave with my boundary. That is my control volume. Stuff come into that box and leave. Before the shock, after the shock. And it's so thin because the shock itself is very thin. So what are the forces acting on that small box? No, static pressure or the weight is very small for gases to start with. And on top of that, that volume basically is almost zero. Because it's like shock wave thin. There is no volume inside, so that you could say it's rho g at, or weight times the g, or volume times mass times the g. No. What else? What other forces acting on that small box? Friction, pressure force. Excellent. So P1 area 1, P2 area 2. All right. Some of you could actually also say, well, how about those two surfaces over here? They are so thin, there is not even, so you don't have to worry about what the pressure value over here even. All right. So then this is our inlet, and this is our outlet. Stuff come here, stuff leave over there. All right. And so let's clarify one thing. So there is V1 normal, V1 tangential, V2 normal, V2 tangential. That's a velocity, right, component. So we can define also a Mach 1 normal and Mach 1 tangential, right? It's basically V1 normal over A1, V1 tangential over A1, and M2 normal, that's V2 normal over A2, and M2 normal over A2. Is there any A1 tangential and A1 normal? Is there such a thing? The flow before the shock wave, is it possible to have A1 normal and A1 tangential? Basically, I'm asking, is there T1 normal and T1 tangential?
No.
There is no such thing, right? There is no such thing as T1 in this direction and T1 in that direction. It's just T1, that's the temperature before. So hold that thought until you graduate. Once you go to a master degree, you realize that no, there could be T1 in that direction and T1 in that direction. All right? That will blow up your mind when you go to your compressible graduate course. You realize that, wow, there is actually, how is that possible? But for now, forget what I said. There is only T1 before the shock, and there is no direction in the T1. Is there B1 normal and B1 tangential for the pressure?
Pressure, yes.
No, it's still the same pressure value. The pressure on that wall could be different from the pressure on that wall. I mean, the pressure on the ceiling, is it different from the pressure on the wall?
Yes.
No, it's not. Forget about the hydrostatic pressure. Assume the whole thing is basically at the same elevation. Is the pressure on the ceiling different from the pressure on the wall?
No.
Right? It's the same. The pressure,
Oh.
P1, doesn't really, there is no P1 normal and B1 tangential. It's just P1. Okay?
Understood your question.
Right. Again, this will hold only until you get your bachelor degree. Once you go to grad school, you realize that no, the pressure actually can be different on the ceiling and from the wall. Right? It will happen on a very weird situation. That's not the normal case, but you can do that. Okay? But for us, over here, there's such only P1 and only T1. And the same thing after. So in this place, after the shock, there is only B2 and there is only T2. Okay? Does this make sense? But we can define M1 normal and M1 tangential because it's the different velocity component. All right? So he would write the momentum equation over here. So first he will write it in, maybe I need the sketch with me. So let me take this so that we can see it. I'll make it smaller. be like this. So he will write the tangential momentum equation. It's basically in the direction of along the shock line. So there are no pressure on the shock line, right? Because the edges is so thin, and P1 and P2 they are all normal. So when you write the tangential momentum equation, you get zero forces. That's zero over here, equal to m dot v out minus m dot v in. Here's the inlet. So what's the m dot coming in? Rho AV. But what V? Remember when we calculate m dot in chapter 1, we said m dot is rho AV. Which V we should use?
Normal too.
Normal. It has to be normal and relative, but it doesn't matter here, the relative part. It has to be normal. So that's for m dot, it has to be normal. So that's why it's rho 2 V2 normal area. That's the m dot part. Which, if you write it at the inlet, rho 1 V1 normal area, they are the same, so they can cancel with each other. Here is the V out and here is the V in. Which V out? Only the component in the momentum equation direction. If you're writing the tangential momentum equation, you wouldn't pick the whole V2. You only pick V2 tangential. And you pick V1 tangential. So canceling m dot with m dot, realizing there is no forces, that basically suggests that V1 tangential equal to V2 tangential. That's the first thing that in the oblique shock wave we have to realize, that the tangential component is not being reduced by the oblique shock wave. The tangential component of the velocity, let's have the better sketch. The tangential V1 and V2, they are equal. It's like the tangential component is having a free ride through the normal shock wave. They don't pay anything. That immediately explained to you why the flow after the oblique shock wave could be supersonic. Because the normal component, we'll see right now, it will suffer a huge reduction in the velocity. But the tangential component of the velocity V1t is exactly the same as V2t. So depending on the angle, maybe the whole flow is almost like V1t and V2t. And therefore the whole flow, it's almost as if he having a very small normal shock wave. The majority of the velocity is just passing by without any reduction. Okay? So this is just from the tangential component. And so of course notice that although V1 tangential is the same as V2 tangential, that doesn't mean, that's a mistake that some of the students do, it doesn't mean that M1 tangential is the same as M2 tangential. When you compare those two guys, even with the same velocity, it's not the same Mach number, because T1 and T2. T1 and T2 will not be the same. You can bet that after the shock, the temperature would be higher or lower? Higher. So that changed the M2 tangential from M1 tangential. All right. The continuity equation. Stuff coming in will have to be equal to the stuff leaving. Why? No storage. Box is so small, steady state, right? So V1 normal, rho area 1 equal to V2 leaving, V2 normal area rho 2. So that's the first equation, continuity. Momentum equation, normal momentum equation. But we'll have to have this box again. Let me put it here. In the normal direction, we have two forces now. We have plus P1 area 1 minus P2 area 2 equal to m dot V2 normal minus m dot V1 normal. Okay, cancel all the areas with each other. You got P1 minus P2 equal to rho 2 V2 normal minus rho 1 V1 normal. Energy equation, this shock is adiabatic. Normal shock, oblique shock, both of them adiabatic. They are not isentropic. They drop the hell out of P naught. But they cannot mess with the T naught. The T naught remain the same. Why? Because there is no heat transfer out of it, right? It can dump the kinetic energy into heat, but nothing really leave outside that box. So because of this, Q is 0, work is 0, and you get basically that the enthalpy plus kinetic energy equal to the enthalpy plus the kinetic energy. Alright? So now H2 plus V2 normal. I split V2 into what? V2 tangential plus V2 normal square. Look at this triangle over here. Ouch. What did I do? I just wanna. So at this, basically over here, I'm trying to say that because V1 has those two normal components, V1 tangential and V1 normal, out of this triangle, basically V1 square will end up being V1 normal square plus V tangential square. So of course then we can split V2 into V2 tangential and V2 normal, cancel the tangential with each other, you will end up with basically those three equations now. Now I would like you to open chapter 4. Go back to chapter 4 and find out where those equations were in chapter 4, the equivalent equation. And that's on page 150, 130, 113. So look at the equation of 113. Those are equation 4.4. And look at those equations. And tell me what you see. Equation 4.4 on page 113. They are the same. They are the same except what? Huh? They are the same except what? What difference do you see? Right. Rather than saying V1 normal, you have V1. Rather than saying V2 normal, you see V2. Right? But the pressure is the same. The H also reads the same. So what? I would like one of you to invent the solution method right now. So what if they are almost the same except for V1 normal replaced by V1? What do we do? What's our job? We want to solve the oblique shock wave. I would like to get M2. Okay? I want you to find out for me how I'm going to get my V2.
Do we know the angles?
Yeah, we know the, let's say we have the angle, we have the delta, we have the theta. And we have M1, I just want to get M2. And this is your clue. Those equations look almost like the equation in chapter 4, except for V1 normal, it's replaced by V1. So for a free homework problem, I'll give Jason the first demo.
Multiply times cosine theta.
Multiply what by cosine theta?
V1.
So V1 normal actually is V1 sine theta, by the way, right? If you remember from the first slide we had, V1 normal, was that true? Let's go back. Here, V1 normal is V1 sine theta. So what do you want to do for us? What are you suggesting? Why don't you multiply by cosine or sine or anything? What are you trying to do?
Take the x component out of.
So you are trying to get rid of V1 normal so that you will end up having V1? Is that what you're trying to do? Huh?
I'll tell him he didn't qualify. But do you just set the equations equal to each other and solve for your unknown?
That's the clue. Like, what's your name?
Christine.
Christine is saying the equations are almost the same. So then what? And by the way, what is the solution for the equation in 4.4? Where is the solution for equation 4.4? Table C. So can we, my question for you is that, basically, can we use table C? Because table C is the solution for equation 4.4, which almost look like this one. So table C, which is, will give you, it has M1 here, it has M2 here, it has B2 over B1, and T2, that's table C. Can I use this to solve my oblique shock wave?
Yes. Yes.
How?
Because they're doing their normal, so you just substitute it in as your B, and you use that.
You are almost there, so no one gets you. You are almost there, but yes, we can use appendix C if we do what exactly? What did you say? Replace what by what?
Your B, your B2. Where there's different, they're pretty much the same, so use the same equations, but you would plug in your B
So here is appendix C. Tell me how we should use it. It has M1, M2. I just, M1 is 2. Wait. M1 is 2, M2 is, I don't know. This theta is, say, 40 degree, and this delta is like 10 degrees. What do you want me to do? How can I get M2 out of this? That's the trick I'm asking for. What does it take to use this?
It takes a normal.
Go ahead.
Charles.
Oh, it takes the velocity has to be normal to the shock wave, and that appendix C, chapter 4, was all about normal shock waves.
So what?
So we can use the same.
So you're saying let's read at M1 equal 2 and read M2?
Yeah. Should be able
Well,
to.
it works if you use M1 normal and M2.
That's
That what?
oh M1.
That what? That's the normal. You what's your name again? Huh? Bradley gave the free homework because he said use M1 normal.
Half. Do we have?
No. M1 normal. M1 normal is the one going through the normal shock wave. See, the equation almost look the same except that it's not V1 that's doing this, it's V1 normal. So V1 normal is equivalent to V1 in chapter 4. So when you look at appendix C now, in this chapter, and that's what all the students' mistake is in this chapter. They would think that M1 is our M1. No, that M1 is not our M1. When you look to this appendix now in chapter 6, your eye shouldn't see M1 here. It should see M1 normal. And this shouldn't read to your eye M2. This actually is M2 normal. Excellent.
And you can do the same thing with the tangential.
So the tangential does not exist in that table.
Yeah.
And this B2 over B1, that's correct, we can use it. The T2 over T1, that's really the T2 over T1, we can use it. All right? So what I'm trying to say is that the mistake that the students think is they will look to that appendix and think that's our M1 and that's M2. But no, they are not. They are actually M1 normal and M2 normal. Okay? Why? Because the equation are almost the same except the velocity is V1 normal.
So that would be your V1 cosine? That's what you're
Excellent. So M1 normal, this M1 normal, so in order to solve this problem then, for those numbers, M1 is 2 and theta is whatever, I will have to say, well, to calculate M2 normal, I need first to find out which row I am in, right? So M1 normal would be M1 sine theta. Why is that? Because M1 normal, that's V1 normal over A1. And M1, that's V1 over A1. And so we know that V1 normal is V1 sine theta. So from M1, you calculate M1 normal. And so that number now would be 2 sine the 40 degree in this problem, for example. You calculate this. And you come here, not at 2, it will be probably lower. And you read this value, and you get your M2 normal. Now, of course, to get M2 out of M2 normal, we have to think about how to solve that. But what I really need to stick in your head right now is that, because that's the big mistake that people think, that when you look to this table now in this chapter, it doesn't say M1 and M2. You should think about it as M1 normal and M2 normal. Right? So every time we solve an oblique shock wave, we will go back to chapter 4 table or appendix C. We will use it again. But we will use it with looking at this as M1 normal and M2 normal. Yes, Brad?
If you give just M1 equals 2, could you just find M1 normal and M1 tangent, use the table to get M2 normal, and then just add M1 tangent to it to get your second?
So
Same-
if you remember,
same.
Bradley's question is, can we say that M1 tangential is the same as M2 tangential since the velocity is the same? No, they are not. Why?
Because T is the same.
Right. So though the velocity is the same, the 2 Mach number in the tangential direction is not the same. You'll figure how to get M2 normal, sorry, M2 total right now. All right, so again, the thing to remember is this the same appendix C that we used, we will use it now, but this will not be M1. This will be M1 normal. Right? And this M2 is M2 normal. That's what you'll get from that table. Is that understood? Because that's where students basically fail to solve those problems. You got it? All right, very good. So now, will we be able to use B total 2 over B total 1? I said we will use B2 over B1 and we'll use T2 over T1. We can use them. Why? Because, I mean, look at this. Those are the same equation. They produce the same results from chapter, the same results that end up generating chapter 4 appendix will probably come out here. So that's why we can use the T and the P ratio. But how about P total 2 and P total 1? Think about it.
Tangential component throws it out.
Yeah. So
Your stagnation property different.
very good. So John is thinking that this probably will get screwed up, because if you remember, how did they calculate this in chapter 4? This P total, this guy is B naught 2 over B naught 1. How did they calculate this? If you remember, it has B2 over B1 and then B1 over B2 and then sorry, what did I say? B naught 2 over B2 and then B2 over B1 and then B1 over B naught 1. And they got those two guys from B and B, appendix B and appendix B, using M2 and M1. And they get this from the normal shock equation, just the one that's over here. So this will hold if you are using now M1 normal and M2 normal. This equation will hold. That's the right P2 over P1. It's okay to use. But those two numbers, if you play with M1 normal and M2 normal, they will not be right. Okay? So, of course, those will get screwed up. Because P1 and P naught 1, even in an oblique shock wave condition, here, before the shock, P1 and P naught 1, how they are related to each other? They are related to each other by M1. P naught 1 over P1 is 1 plus gamma minus 1 over 2m squared. They don't care about the shock at 40 degree or 30 degree. They are still static and stagnation of that supersonic flow. So they are related to each other by M1, not by M1 normal. And after the shock, P2 and B naught 2, they also don't care where the shock is sitting with respect to them. They are related to each other by M2, not M2 normal. So what I'm trying to say is that now in oblique shock, when we are solving it and we are using that table and we are reading M1 normal here so that we can get those guys, this number should be wrong. Correct? For the reason that I explained right now. However, it actually will end up being right. You can use it. How is that possible?
It corrects itself.
Right, it corrects itself actually. So two mistakes fix themselves. And every year I basically give this as an extra homework problem for the student. I tell them if you get it, then you get a bonus basically. And every year maybe only one student can get it right. And by get right, I mean mathematical proof that this ratio multiplied by each other is correct, whether you are using M1 normal, M2 normal, or using M1 and M2. Exactly. The division holds whether it's basically the normal velocity, normal Mach number, or the total Mach number. All right. So at the end of the day, what I'm trying to say is that you can use all those guys for an oblique shock wave if you enter M1 normal here. That's very convenient. to get the ratio of the P naught across an oblique shock wave. However, this last column is a no. You cannot use this last column, the one that we used to solve the quiz with, the P naught 2 over P1. That doesn't work for an oblique shock wave. Why? Because it will involve only one mistake, Only one mistake, it will not fix itself. It will only involve those two guys. So does this make sense? So for oblique shock wave, you can use all those guys. Again, if you use the right M1 normal, M2 normal, and you will not be able to use the last one. Okay, questions? So let's see how we solve a problem like this. So here is the pressure before the shock, P1 and T1 and M1. And he is asking for M2, B2, T2, and delta as well. So let's solve for P2. How can I get P2 if I know P1? Anyone? You given P1 and M1, and he's asked for an oblique shock wave at an angle 40 degree, and he's asking for B2. How can I get P2? The pressure after the shock.
M1 cosine 40 degrees.
No, you are saying M1 sine.
Or sine.
So first you will get M1 normal as M1 sine theta. Right? The 2 sine the 40 degree. Alright, and then what do you do once you get that number? Use table C with this M1 normal. And this will allow you to get B2 over B1. And once you have this ratio, and you know P1, you calculate B2, right? Got it? How about T2? The temperature after the shock, if you know the temperature before the shock. Same thing, right? You will also get, from M1 normal, you will get T2 over T1. You know T1, you can solve for T2. Okay? How about M2? Let's get M2. We didn't get M2 yet. How are we going to get M2? What does appendix C give us? M2 normal, right? This appendix C can give you the pressure ratio, can give you the temperature ratio, it also can give you M2 normal.
Divided by sine.
So M2 normal and M2 are related to each other by sine theta minus delta. So notice M1 is much easier. M1 is actually, M1 normal is M1 sine theta. But M2 normal is a little bit complicated. It's because of this. It's sine theta minus delta. So we don't know delta. As a matter of fact, he's asking for delta. So what's the plan? Yes, you can get M2 normal.
Take the M2 out of the table and then divide by B2 and do the arc sine.
Say that again slowly.
Take the M2 normal out of the table.
Yes.
Divide it by the B2. And take the arc sine of that. And you can easily solve for delta because you know theta.
So you're saying get V2 first, right? How can I get my V2? V2? You are saying let's get V2 tangential then. You are saying let's first get V2 normal and then get V1 normal equal to, sorry, get V1 tangential equal to V2 tangential. So basically get the two velocity component and out of this solve for M2. That's one way. But what else is available for us to get M2?
Appendix D. Or we still trying
Not
to get
yet.
D?
Not yet. So before we introduce appendix D, you can get M2 for me right now. For a free homework problem. How we can get M2? Huh? I can't hear. And forget about theta and delta for a second, because I cannot mess with delta because he asking me for delta.
Couldn't we just do vector algebra because the velocity in the tangential direction is the same?
Forget about the direction, velocity, and all those things. We need to calculate delta later. Huh?
Which is the tangential squared plus the normal squared.
Forget about all the velocity component. Give me M2 from something else.
Your temperature ratio,
You had a free homework problem. The temperature ratio, T2 over T1,
Doesn't change.
T naught 2 over T naught 1 does not change. And therefore you have T naught 2 and you have T2. You have T naught 2 from T naught 1 and you just calculated T2. So out of T2 and T naught 2 you can calculate M2. Notice how P2 and P naught 2 and T2 and T naught 2, they are still related to each other by M2. Not M2 tangential, not M2 normal, the whole M2. Right? So another way to calculate M2, it's not the best way, it's not the fastest way, but another way is to calculate the T2 and T naught 2. And out of that you can calculate M2. Alright? So here is the dilemma that we have, that basically once you calculate this M2 normal, which is M2 sine theta minus delta, you have two unknown, how you can calculate M2, and therefore the temperature is one way, using T2 and T total 2, which is the same as T total 1, which even if T total 1 was not given, you get it from M1 and T1. Appendix B, M1 and T1, you calculate T total 1. And then with two of those guys, you can get M2. Now with M2 normal and M2, you can calculate the delta. Knowing M2 normal from from Appendix C, knowing M2 from this calculation over here, you can calculate the delta. This is a very long process. It doesn't work that way. And besides, when you think about it, the problem is never, we are going to have a shock wave at 40 degrees. Now, I wonder what our airplane will look like. No, you actually have the airplane, you have the delta, and you are trying to solve the flow over it. So the scenario is that you know delta, and you know M1, and you would like to calculate M2 and theta. Of course, theta is very convenient to solve the problem with, because once you have theta, you have M1 normal, your normal shock table open for you. So that you can get the pressure ratio and temperature ratio, right? So really, here is the key message that you need to remember today, that knowing theta and M1 turn the oblique shock problem into a normal shock, right? Knowing M1 and theta turn the oblique shock problem into a normal shock problem, because basically it puts your hand on M1 normal. And once you have M1 normal, that's basically your key to using that normal shock table. So obviously, people who don't know how to use a normal shock table will never be able to solve an oblique shock wave problem. Because, I mean, that's the first step, to get M1 normal, then use a normal shock table. So you have to be very comfortable solving a normal shock to start with, right? And you need your theta to be able to use that table for an oblique shock. What I just explained right now is that having the theta is not always given, when you're designing a new wedge and you don't know what theta is. So the equations are not really written in a way that will help us to get theta, right? It will require trial and error. So as a result, basically they will have to help us with another way to get this theta, all right? By the way, so this is the extra homework problem that I was telling you, right? So please prove that for an oblique shock wave, this is equal to this. What is that? That's basically the ratio of, can anyone recognize what's that? This is B naught 2 over B2 multiplied by B1 over B naught 1. And so this is the ratio for those value using the M1 and M2, and that's what will happen if we end up using the normal component, M1 normal and M2 normal. And so we are saying that, yeah, it's okay, you can still use those two columns, the B naught 2 over B naught 1. Why? Because this should be equal to this. So if you can prove to me that this is equal to this, you get one free homework problem. All right? To prove that this equal to this. And I don't want you to tell me that, Well, it's because the temperature remained the same, therefore the acoustic speed remained the same, and I don't want you, I want you to start from here, drive this, or start from here, prove this. I mean, start from left hand side, drive the left, or drive from the, start from the left, drive the right. You got it? Very good. So now, how is it going to help us getting the theta if we actually know the delta? Because that's what will be the normal scenario. It's appendix D. All right? So appendix D basically have those chart where on the x-axis you have the delta, that's what you know, and on the y-axis that's the theta. That's what you would like to calculate, so that you put your hand on. Why do you need theta again? Why do you need the theta? Because M1 normal. Because you want to calculate M1 normal so that you can use the normal shock table. So reading delta here and all those graphs, what are those graphs for? Those are for different M1. Okay? So knowing M1 equal to 2, for example, you will be able to calculate theta. Unfortunately, M1 actually curve is like this. So you will hit M1 twice. You can hit it here and that produce one theta. You will hit it here and you produce another theta. So the upper curves, they are separated by that dotted line between, or dashed line. So this is the strong shock and this is a weak shock. So there are two solutions that's possible for the same delta. So if Mach 1 equal 2 and delta say equal 5 degree, you can make this shock or that shock. If you can notice that those are all approaching 90 degree, what's that? That's a normal shock. That's their basically asymptotic solution. It will be like a normal shock standing in front of the, and those are approaching different values, not 90. So all those graphs, they end up going at different value. So what do you think those things are? Those angles are what? Physically, what they are? Huh? Yeah, of course, they are all theta. That's on the y-axis. But what are those values?
The angle of the nose? Or
No, it's not that as, how can I go there? You go there by when delta is equal to, delta equal to what? Huh?
0.
0. This is delta 0, this is delta bigger, like higher and higher delta. So when delta is 0, those different Mach number produce different theta. I'm talking about something thin like this, flying supersonically. And this is the theta he's generating. So why the value here is different from here, different from here, different from here? For a free homework problem, what are those numbers?
The faster you go, the more streamlined you are.
I know, but what are they?
That's the angle of the shot. I mean, there wouldn't be an angle if you're going.
They are the angle, but they are also something that we had studied before.
Drag coefficients.
They are angles of something we studied before. Huh? It's not called the Mach number, it's called Mach angle. And Tim had a free homework problem. It's the Mach angle. Do you remember it from chapter 2? Right? When we had a very small thing flying, a small disturbance flying, and it generated mu, and the mu was what? Sine minus 1 over m. Those are the mu's. Right? So for different Mach number, each one of them is going to its mu. Right? That's because, I mean, delta is 0. You are flying basically a piece of paper at that Mach number. So depending at this Mach number, you will generate the mu. This is very important. This actually tells us that then if delta is not 0, if I'm not flying a piece of paper, but flying my engine or something, I'm not going to generate my mu. That mu was only for a piece of paper flying, 0 disturbance. But if you fly a wedge of 5 or 10, or what do you generate? You generate higher and higher angle. That is a shock wave angle, theta. So an F-18 flying will not generate mu in front of it. It will generate the theta in front of it. Right? Now what's the deal with those two branches? Why, for still zero, a piece of paper flying, why you can generate the mu, or you generate a normal shock wave at 90 degree? That's what this thing is. It's either the mu or 90 degree. It's either 23 or 87. It's why there are those two solutions. We'll see in a second. But Yang had a question first.
Oh, I was gonna ask, why does it stop like at 46?
That's excellent question. So Yang is concerned about this. What if your delta, ouch. What if you come here, huh? And delta is, bigger than this max. This maximum is what, like almost like 23 something? How much is it? The delta max, the last one that we had. 45?
Yeah,
Right.
just after.
So this is like, let's call it 45. What if it's delta 50? Why? The fact that we don't hit the curve mean what exactly?
It hasn't been calculated on here.
It means there is no solution. What? What do you mean there is no solution? There is no oblique shock solution. So I would like you to imagine that scenario basically. What's happening? So let's have the same.
It's outrun the shock wave.
Let's have the same Mach number. So we are on the same curve, this M2 curve. And as delta is 0, you generate the mu. Good. You increase delta, what happened to the angle? Get bigger and bigger and bigger. As you increase delta and delta, as the wedge basically get bigger and bigger, delta become bigger and bigger. Sorry, theta become bigger and bigger until delta hit the max,
And it's a normal shock.
and it will be a detached shock wave outside. Detached normal shock wave. It will not be an oblique shock wave. So when they land, anything from space in re-entry, they make sure that the bottom have bigger than delta because they don't want an oblique shock that will eat your nose and burn the whole thing. They want it to be outside,
Use the air itself.
detached out from it.
So it uses the material in front of it as insulation.
That's another thing. They try to make the material also diffuse so that it can send some kind of like flow out of it so that it prevents the flow from coming to the nose. So back again to this. So this chart is very useful for us because if we know delta, we will be able to get theta out of it. All right? So it looked like this. Weak solution, strong solution. And we didn't really answer yet why would we have this or that. But we could have the weak or the strong in a second. There is actually 3 tables in our book. D1, D2, D3. D1 for 1.4, D2 for 1.3, D3 for 5/3 or 1.67. For a free homework problem, anything wrong with those guys? And anyone who had free homework problem today doesn't qualify for another one. We're looking for a new winners. Do you see anything wrong? What's wrong?
This one on the end.
What about it?
There's no place for that oblique shock that you're talking about.
That's a good notice, but I want a more probing answer than this. Ethan basically had his eye on the right place. That graph is weird, but he's basically saying, so why? So let me try one more time with you. So why do you want to see the nose? He's saying, why I don't see the nose? Why do you want to see the nose? Why you expect it to be there? Let him answer for a free homework problem. So why do you expect to see the nose? Because what? Why? You should see the nose because
It doesn't make sense for there not to be an oblique shock wave.
yeah, it doesn't make sense, right? Because so 1.4, 1.3, 1.67. because 1.67 actually need to be on this side. So actually, if at 1.3 the maximum is like almost 50, and at 1.4 the maximum is almost 45, at 1.67 one should expect the maximum to be not at 70. See, the fact that we don't see the nose doesn't mean it's here. It's not here. It's basically say that it's a little bit to the right, out of the chart. So actually 1.67 should, based on that trend, Mother Nature basically should put it at, I don't know, like 35 or something,
They're out of proportion.
right? So this actually is wrong. This is actually is wrong. The actual correct graph should look like this. It should be at around, the nose is around 35. So actually I called the author and I told him, are you aware this chart is wrong? And he said yes, the chart is wrong, and they will fix it in the next edition. They are trying to make a new edition. Hopefully it will show up later. But so for us,
You know this is wrong.
this for us, we will never use a figure D3, and therefore D6. There is also D6, that look like. So don't use D3 or D6. They are wrong. They plotted them wrong. All right. Actually, they plotted them for a gamma equal 1.001. So basically, the gamma should read. So who care about 1.0001? Okay. But anyway, so it's wrong label. Don't use it. And we are done for today. Thank you so much.